Alright, section 3.4 deals with solving both exponential and logarithmic equations. First we'll start with exponential equations, one of this nature. 2 to the x plus 3 equals 32. I have it written here 2 times because there are two separate ways that this can be done. Those two methods are, one is you can try to get the base on each side to be the same. The other method is to use logarithms. Now when you're trying to get the base the same, it's got to be something where it's going to be something recognizable. If it's not, then I would probably revert to number 2 most often. But in this case it should be somewhat recognizable, because 32 can be written as 2 to the 5th power. And so since we have 2 to the x plus 3 equals 2 to the 5th, the bases are equal to each other, and if the bases are equal, and there's an equal sign in between them, then the exponents must also be equal. So then we can just write x plus 3 equals 5. And then solve this equation for x by subtracting 3 and getting x must be 2. Now, like I said, the other method you could do is to use logarithms. And to get rid of 2 as our base, we would have to write log base 2 and log base 2 on this side. And then because of our properties of logarithms, our exponent gets moved out in front as the multiplier of what log base 2 of 2 is, and we know log base 2 of 2 is 1, so 1 times x plus 3 is x plus 3. Now on this other side you have log base 2 of 32. And if you did not know that 2 to the 5th is 32, remember you can always refer to your change of base theorem and take the ln of 32 divided by the ln of 2, or log of 32 divided by log of 2. Either way, if you do it one of these two ways, or using your property of logarithms saying 2 to what power is 32, you're going to get 5, which is the exact same thing you get here, and then subtract 3 and get x equals 2. Alright, so our next example is 3 to the x plus 5 equals 12. In this case, there is no way to write 12 as a base of 3. Well, there is, but it would be very difficult to figure out. So instead, you would just want to use the other method and take log base 3 of both sides. And then this turns into 1, so 1 times x plus 5 is x plus 5. And then using your properties of logarithms, you would take the change of base property, log of 12, divided by log of 3, which is approximately 2.261. Now at this point you should not round this number in your calculator. Here's where you need to make sure you understand how to use the ANS button on your calculator. And if you don't know how to use that at this point in time in your mathematical career, good luck to you in the future. So then at this point, you would have to subtract 5 and get x is approximately equal to a negative 2.738. And then you would be done. Now a couple of other examples using that same type of logic. In this case, because we have 10 to the x plus 5 equals 12, same thing. We would want to get rid of the base of 10, so we would say log base 10. And remember, when there's a base of 10, that is a common logarithm. And we do not have to write the 10 down here because we have a button on our calculator that will do this for us. And we do not need to use our change of base theorem. So we would just write log of 12 over here on this side, punch that into our calculator, and get x plus 5 equals, and this again would be approximately equal to, and it's 1.079. And again, here's where you need to understand how to use the ANS button later on. And so here we would subtract 5 and get a final answer of x being approximately equal to a negative 3.921. If we have something with e to the x plus 5 equals 12, then to get rid of a base of e, we would use log of base e, but we do not write log of base e, we write ln, natural log of both sides. And this side, still the same thing happens. You would get x plus 5 because the ln of e is 1. And then we have to figure out what ln of 12 is, and that is approximately equal to 2.484. And again, subtracting 5 from both sides, you would get x is approximately equal to a negative 2.515. And that would be solving exponential equations. So then, moving on to solving logarithmic equations. In this first example, this is similar to the problem we did at the beginning, where we had 2 to the x plus 3 equals 32 when we first made the bases the same. And so since the bases were the same, we could set the exponents to be equal to each other. Well, when solving a logarithmic equation, if you have logarithms with the same base, that same concept applies to this type of problem because of this fine equal sign. So because these are the same, we can just get rid of them and say that x plus 4 equals 2x minus 5. Because if the bases are the same, then these have to be the same. And so now solving this, we would subtract 4, subtract x, 2x, get a negative x equals negative 9, and then take the opposite of both sides to get x equals 9. Now, the one thing you have to keep in mind when solving a logarithmic equation, which is a little bit different than solving an exponential equation, is in a logarithmic equation, the domain of any logarithm is, the domain has to be greater than 0. So that means that anything you substitute into this particular part of the logarithm must be bigger than 0, because if it's not, you cannot take the log of it, no matter what the base is. Same thing has to happen here. If you take this value and substitute it in, it must be greater than 0, which in this case it is, because 9 plus 4 is 13, and 2 times 9 is 18 minus 5 is also 13. So this solution does work. There are going to be times when it doesn't. When that happens, it is called an extraneous solution. And an extraneous solution is a solution you get when solving that doesn't work in the original equation. So if this happened to be an extraneous solution, we would cross it out, and then there would be no solution that would work for this particular equation. Like I said, this one does, so we don't have to worry about it. But you do need to make sure you check to see if it's going to be an extraneous solution by substituting into every place where the variable is and see if you get something that is greater than 0. Now our next example is another logarithmic equation, but this time there's only one logarithm. So here, you just have to understand the meaning of it. And by that I mean knowing what the base is, where your exponent is located, and what it's supposed to equal. Because when you have it with just one logarithm, you need to rewrite it as an exponential equation. So we know 4 is our base, 5 is the exponent, and it equals 2x. And then it's just a matter of solving this. So dividing by 2 and dividing by 2. And so x is going to be 512. And now if you check this number into this original equation, if you put 512 in, 2 times 512 is greater than 0, so it does work. No extraneous solutions. If our equation starts out as ln of 2x equals 5, then we would write e to the 5th equals 2x. Still would have to then divide by 2, except now you'd be taking e to the 5th and divide it by 2, which in this case would be approximately equal to 74.206. And since you have a natural log problem like this, you could also have just plain old log 2x equals 5. In this case, our base now is 10 to the 5th equals 2x. Divide by 2, and x would equal 50,000. So that's when you have just one logarithm in an equation. Last type of logarithmic equation would be something like this, where you have more than one, and if you try to move one to the other side, you would still have 2 plus log base 3 of, or 2 minus log base 3 of x plus 1, or 2 minus log base 3 of x, either way. So you wouldn't just have an equal sign between two logarithms like the first one, where you could set each part equal to each other. So in this case, when you have more than one logarithm, here's where we have to condense it. And so, by our properties of logarithms, if you're adding, that means you multiply, so you would have log base 3 of x squared plus x, because you have to multiply those two things together, and that would equal 2. And then from our understanding of logarithms, 3 then becomes our base, 2 becomes our exponent, and x squared plus x is what it has to equal. Simplifying this down, 3 squared is 9 equals x squared plus x. Subtracting 9 from both sides, will leave us with 0 equals x squared plus x minus 9. And now if you can factor it, do so. Which, are there any factors of a negative 9 that will add up to 1? No, there are not any. So we have to turn to our formula, and we would write then a negative 1 plus and minus square root of 1 squared minus 4 times 1 times negative 9 all over 2. And that's what x has to equal. Now then, if you simplify this, 1 squared is 1. 4 times 1 times 9 is 36, and since there's two negatives, it becomes 1 plus 36. So now we would have a negative 1 plus and minus the square root of 37 all over 2. And so, if you convert these two answers to decimals by taking a negative 1 plus the square root of 37 over 2, you will get an answer of 2.54, rounded to the nearest hundredth. If you take a negative 1 minus the square root of 37 over 2, you will get approximately a negative 3.54. And so now, if we go back to the original problem, if we substitute 2.54 into this, that's still greater than 0, so it's okay. If you substitute it into that, it's still greater than 0, so it's okay. So 2.54 is a solution. If we look at the other one, negative 3.54, if you substitute that in for x, you'd have log base 3 of a negative 3.54, which is not greater than 0. So therefore, this solution would be considered extraneous, and we would cross it out. And the only solution that we would have then would be 2.54. It is not always going to be the case where the positive one is the solution and the negative one is not the solution. It all depends on what the equation is. Sometimes both of the answers may work. You may even get one where this could become x cubed and all of that stuff after x cubed, where you'd have to use your synthetic division and your L thing to find the 3 roots and then check all 3. And that concludes this lesson on solving exponential and logarithmic equations.